In the previous lessons leading up to this lesson, we've learned that there's a lot of different forces that can cause centripetal force. Centripetal force is the force that causes an object to turn. And we're especially interested in centripetal forces when an object is moving in uniform circles. Uniform circular motion has some specific equations that we can use that help us understand the motion of the objects moving in circles. Those two equations, namely, are the centripetal force acting on an object can be calculated by mv squared over r, or 4 pi squared mr over t squared. Those are our two equations for calculating centripetal force. But we've learned a lot about solution strategies for centripetal force, centripetal acceleration problems, in that these objects that are moving in circles, because of the centripetal force, that centripetal force is always caused by another type of force. It's not a force in and of itself. And because it's always caused by another type of force, we can identify that force that's causing centripetal motion, uniform circular motion. And once we identify that force, we can set the equation for that force equal to our equation for uniform circular motion. And we have to get creative, we have to simplify, we have to cancel things out if they appear on both sides of the equal sign, both in the numerator or both in the denominator. And then we solve for our unknown variable. Well, this lesson is going to be a continuation of learning about how these specific force problems are set up. In the previous lesson, we learned that celestial objects oftentimes will experience gravitation as a centripetal force. And there are a bunch of different ways to set up equations to solve for different variables using universal gravitation set equal to our equations for centripetal force. And the same thing applies to the motion of objects that are moving around banked curves in uniform circular motion, like a car making a turn around a perfectly circular quarter circle corner, and the turn is banked to help the car move around the curve. That's the sort of motion we're going to learn about in this lesson, uniform circular motion on an incline, and the incline is actually the bank of a turn that uses part of the normal force to help cars make it around a curve, or to help marbles roll around a circle, or to help anything use the slope of the surface that it's moving on to help it turn a corner. Okay, we're actually going to learn this lesson in the context of a practice problem. Here's our practice problem. A curve that has a radius of 100 meters is banked at an angle of 10 degrees. Can a 1,000 kilogram car navigate the curve at 125 kilometers per hour, or 77.7 miles per hour? That's pretty fast without skidding. Now, just initially, I'm looking at this problem. 100 meters isn't really that big of a radius for a curve that when you're driving in a car. And 10 degrees is a very, very small incline for a banked curve. So my initial thought here is that this car is going to go skidding off the roadway because there's no way it'll make the curve with that speed and that tiny bank incline. However, the rest of the problem gives me hope. The road surface is dry asphalt with a coefficient of static friction equal to 0.850, which is a large coefficient of friction. That's what you would expect it to be, though, because we're talking about car tires on a road surface. Car tires are made so that cars don't easily slide around on the road. They're made to have good traction. So maybe this car will be able to make the curve. We're going to have to work the problem to find out. But before we get started, I'm actually going to adjust this problem and work it to start a little bit unlike the directions say. Let's imagine that there is no friction. We'll say that this curve is iced over and this car is going to go driving over it without that friction force. Will it, with a 10-degree angle bank, be able to make the curve? Let's find out. Well, how are we going to start even analyzing this problem? A good place to start with any centripetal motion and uniform circular motion problems is to draw the circle that you're dealing with. So here's a circle. Here's where my car is, and there's a centripetal force acting on the car pointing toward the center of the circle. There has to be for the car to continue to move in a circle. And what I must be doing, I must be looking either down from the top or up from the bottom of the car. It's a little easier to picture looking down from the top because otherwise we're underground. Okay, so picture we're looking down from the top, and that means that the car is moving with a tangential velocity that's a tangent line to the circle, And that tangent line is perpendicular to the radius of the circle at that point. And it's just going to continue moving around and around. The direction of the tangential velocity is going to keep changing following the outside of the circle as the car goes around. Now, we've worked problems similar to how we're going to work this problem before. And there's going to be a tendency of your brain to try to use the concepts we learned in those previous lessons. For example, here's a problem where we have a block sliding down a slope. And this block could be any object. It could be a skier sliding down a slope. It could be a stalled vehicle sliding down a roadway that has an incline. Okay, so you can kind of just picture that this block can be anything, and we're looking at the side of it. The path of motion is either upward or downward, the incline. In this case, you can see the acceleration is down the incline. And you can kind of imagine if the acceleration is down the incline, even if the object is moving up initially, eventually it's going to start moving down the incline and accelerating in that direction. If I have an acceleration in that direction, that means I must have a net force in that direction. Where does that net force come from? Well, for these equations where we had something moving on an incline, keep in mind the path of motion is on the incline. That means that if there's an acceleration, it has to be in the same direction as the path of motion. It's also going to be pointing on the incline. And the way that we solved these problems was we set up our axes so the entire coordinate plane was tilted. But now let's consider the specific case of a car on an incline using the incline to move in a circle. This car is going to have forces acting on it just like the box on the right has forces acting on it. Those forces are going to be the normal force perpendicular to the surface the car is on and the force of gravity pulling straight downward. Now this setup is starting to look an awful lot like the box problem. But you have to consider the direction of the centripetal force. What direction is the centripetal force pulling this car? Is it pulling down the slope? Well, centripetal force always points toward the center of the circle. And the direction of the circle is actually in that direction. It's not down the slope. It's sort of at an angle to the slope. It's horizontal. This car is making a horizontal circle as it moves around the curve. So you'll notice immediately this is unlike the problem where we had a box sliding down a slope. Because in that problem, the direction of motion was in a line that was on the slope. And therefore, we had to figure out a way to get our net force. When we added up the sum of all of our forces, our net force had to be in the direction of the slope. That's why we had to tilt our axis and turn gravity into parallel and perpendicular components and then solve from there. In this case, though, we just need to find a component of something that is in the direction of centripetal force. It can't be gravity, because gravity points straight downward perpendicular to the centripetal force. And if a force is perpendicular to the net force, that force can't contribute to the net force. So if we're looking for that net centripetal force, it has to come from somewhere else. Where might it come from? Well, do you see that the normal force actually has an x and a y component? Do you see how maybe the x component of the normal force could be the centripetal force? Now, before we move on, let's make sure we analyze this problem to see what the angles are, because we've worked problems like this before. Notice on the right-hand side, as I'm demonstrating how we work those problems with boxes on slopes, I know that the 15-degree angle of my slope is also the top angle of my force triangle, and we proved that geometrically in the past. Well, the same thing is true for the angle of this slope and the top angle of our triangle of normal forces. It's not the same exact triangle. Now notice the right angle is on the left bottom, not the right bottom, and it's not tilted so it would set nicely on top of the slope. However, you can see that that top angle is the same in both drawings, and the geometry of it is the same. All right, so now that we have this triangle drawn, we can now express the normal force in terms of Fny and Fnx, as long as we multiply them by some trig function related to that 10 degrees at the top of that triangle. We're going to be using that heavily during this lesson. The next thing I'm going to point out, though, is that we had to tilt our planes before when we worked the problems involving objects sliding down slopes. Here, we're just going to keep the same plane as we have in the problem. So vertical is vertical, horizontal is horizontal. We're not tilting our plane so that the quote-unquote horizontal path is down the slope. Notice that we could do that because we have a force already from our components of the normal force that's pointing exactly in the direction of centripetal force. So we could identify that the x component of the normal force is what's providing the centripetal force for this problem. It's in the right direction. It's the only force that's pointing that direction. When I break down the normal force into components, it has to work. All right, and now I'm just going to use my techniques for solving force problems to get to the bottom of this one. So I'm going to say that the net force is equal to the sum of all of the forces added up. That would be Fny, Fnx. Remember, when I add those two together, they make the normal force plus gravity pointing downward. I'm also going to note that the gravitation force and the y component of the normal force have to cancel each other out. Anytime we cancel forces out this way, we can come back to them later in our problem and note that when we add them together in the correct dimension where they're acting, they must be 0 as a sum because they canceled out. So we'll come back to those. But first, I'm also going to write my other net force equation that I need. My other net force equation is either that force equals ma or force equals 0 if there is no acceleration. Well, there has to be an acceleration here because I have an object moving in circles, which means there's a centripetal acceleration and a centripetal force. So my net force causing uniform circular motion is mass times centripetal acceleration. All right, now let's go back to those forces that canceled out. I know that the size of one force, we'll say that the y component of the normal force, you can see that in the diagram down below, has to equal the size of the gravitation force. Now, I know before in the past we've worked with putting negative signs in front of downward pointing forces. Here I'm going to take another approach, and I'm just doing this for convenience in this problem. There's nothing really special about this problem that made me do it this way. I just want to point out you can note that the magnitudes of two vectors are equal by putting an absolute value sign on both vectors, or at the very least putting it on the vector you know is normally going to be negative. So all I'm saying is that the magnitude of the normal force y vector pointing up is equal to the gravitation vector pointing down. And do I know any formulas for either of these? Well, yeah, I know that the force of gravity anywhere in Earth's gravitational field is simply mass times gravity, mg. I know the mass and I know the strength of Earth's gravitational field, so that's going to be helpful because I can calculate from this the y component of the normal force, and that might help me to solve something else later in this problem. All right, now we're trying to figure out, though, how the normal force is pushing this, because we need to figure out if the car is going to skid. So basically what we need to figure out is if this car is going to make this turn with no friction, it's a 100-meter circle, radius circle, with a bank of 10 degrees, and the mass of the car is 1,000 kilograms. Is this car going to slide off when there's no friction? Is that bank enough? Okay, so let's just kind of keep that in mind. We're given that 125 kilometers per hour value, but we can't just plug that into the equation because that's a value that we're going to use to compare against. We're going to see how fast the car can go, and then we're going to see if the car can go faster than 125 kilometers per hour and still make it around the corner. All right, so I'm going to combine my net force equations, and I find that the centripetal force F net x equals mass times acceleration. There's just one centripetal force. That's happened for a lot of different problems so far, that there's just one force causing the centripetal force. In this case, it's the x component of the normal force. But I don't know what the x component of the normal force is. I do know from my diagram over on the left there that the x component of the normal force is opposite the 10-degree angle. So it must be whatever the normal force is times the sine of theta. And I already alluded to how in this problem we can find the size of the normal force because we know the y component of the normal force is mass times gravity, both values that we know. And we use trig to get to the normal force. The way that I'm going to do that is I'm just going to note that the cosine of my theta in that diagram over on the left, the cosine of 10 degrees, is adjacent over hypotenuse, or the y component of the normal force divided by the actual normal force. Or I can rearrange it so that Fn is the y component of the normal force divided by the cosine of theta. I can go ahead and plug in mg for Fny based on my equivalence up above. I noted that up above that normal force y component is equal to mg. And now I have this expression that I can plug in for the normal force. Fn is mg over the cosine of theta. Well, let's go ahead and plug that into our previous equation we just developed. The centripetal force, remember, is the x component of the normal force, which equals the normal force times the sine of theta. But if the normal force is also mg over the cosine of theta, I can combine those to get mg sine theta over cosine theta. And then one more simplification. A trig identity that's very common to use is that the tangent of theta is the sine of theta divided by the cosine of theta. So anytime I have sine theta over cosine theta, I can just replace that with tangent of theta, and that's what I'm going to do here. The normal force in the x dimension when an object is moving around a frictionless slope is going to be the mass of the object times gravity times the tangent of the angle, the slope of the banked curve. Now, in the true fashion of these uniform circular motion problems, I'm just going to note right now that that x component of the normal force is a centripetal force. And therefore, I can take that force and replace it with one of my centripetal force equations. In general, I could just write this equation. The mass times the centripetal acceleration equals whatever's on the other side of that expression, because that's a centripetal force. And I see that I have the mass of the object going around in a circle times the centripetal acceleration equals the mass of the object going around in a circle times g times the tan of theta. I can cancel out that mass on both sides of the equation. I'm dividing both sides by the mass of the object to cancel it. And I'm left with centripetal acceleration equals g. I know that constant. It's just 9.8 newtons per kilogram or meters per second squared. In this case, meters per second squared probably makes the most sense, times the tangent of the angle of the banked curve. Now I can plug in any of my equations for centripetal acceleration. Do I have an equation for centripetal acceleration that has velocity in it? And if I do, I can use that to find the velocity that I can safely go around this curve without slipping, just because of its slope without incorporating any friction. I do have this equation, centripetal acceleration equals v squared over r, and that's a tangential velocity. And I can go ahead and set these equations equal to one another. Now notice the masses have already canceled. So I already had my centripetal force equations. When I cancel out the masses, now I'm talking about centripetal accelerations, but it's fine because I just want to find the speed at which I can move around this circle when there's no friction and not go flying off the roadway. And that's going to be calculated using this equation. I'm going to get velocity on a side by itself, so multiply both sides by the radius, and then I'm just going to take the square root of both sides, and that gives me the tangential velocity equal to the square root of g times the tangent of theta times the radius. Let's go ahead and plug in some values. I'm going to plug in 9.80 meters per second squared for g, 10 degrees for theta, so the tangent of 10 degrees, and then 100 meters as my radius. And when I simplify this, I find that the velocity at which I can move around this circle is 13.1 meters per second. Now, interestingly, that's the velocity if there's no friction, that I'm going to be moving around this circle of exactly 100 meter radius. If I go any faster than this, I'm going to move in a circle with a greater radius, and any slower, a circle of a smaller radius. Now, just keep that in mind. In the real world, that doesn't happen. You're able to move through turns with a certain radius at different speeds. Okay, so you can take a corner that you think about your drive home. There's maybe a left turn that you take where you move in a circular path around a corner. And you know that you can take that path really fast or more slowly and still move in the same radius. So this situation is if there is no friction, it's not a very realistic situation, but if this curve was covered in ice or if it's really raining, then you would count on the bank to move you around the turn. Hey, let's see how this compares to our comparison value, 125 kilometers per hour. If I take that 125 kilometers per hour and convert it to meters per second, am I going to find that that value is less than the tangential velocity here or greater than? Well, to convert it, I'm going to have to multiply by 1 hour per 3,600 seconds. That cancels my hours. And then we're going to have to multiply by 1,000 meters per kilometer. That cancels my kilometers. And I find that I have a value here of 34.7 meters per second. That is a much larger value than the 13.1 meters per second I'm able to move around the corner and maintain my 100 meter radius. So at 34.7 meters per second, it would be a much larger radius circle if there was no friction. Okay, so that friction is going to be important. Let's see if that friction is enough now. And we know that the friction is substantial. Let's see if that's enough to keep us moving in a circle here. So how is this going to change things? Well, down in the lower left, I need to now add another force into my free body diagram. The force of friction. But which way is that force going to be pointing? Now, if you think about it, in this problem, that force of friction could be pointing down the slope or up the slope. Think about it if I took this turn too slowly for that 100 meter radius. Let's say I went less than the speed that we just calculated. Well, that means that the tendency of the car would be to slide into a narrower circle with a smaller radius. And in order to stop the car from sliding down the slope, there would have to be a friction force applied up the slope to keep the car moving in that wider circle than it could normally move around. So my friction force would be pointing upward in that case. However, if I'm going really fast for the curve, faster than I would naturally be going if there was no friction, then my friction force would have to be pointing down the slope, helping to apply more centripetal force toward the center of the circle. And that's the situation that we have going on here. I mean, if you think about it, if I'm moving at 35 meters per second, but I'm actually able to move only at around 15 meters per second, that means that my curve is going to want to be more like this than that narrower radius circle. And in order to push me back into that narrow radius circle, I need more force pushing inward. That force is going to come from a force of friction. That force is always going to be parallel to the surfaces that are not able to slide past one another. So that force is going to be directed down the slope here. Okay, and let's break that out into components because once again, I need to have forces that are pointing in the direction of the centripetal force. And the centripetal force isn't down the slope, it's horizontal. So I need to break this friction force into its horizontal and vertical components. And it's pretty easy to see that the angle within this triangle is going to be 10 degrees. So that makes this solvable. I can solve for the x component of the friction force in terms of the actual friction force, as long as I'm able to figure out what that actual friction force is using trig functions. And then let's go ahead and replace our friction force in our diagram with components that are pointing in the x and the y dimensions. So we have everything pointing in the same dimensions. Now we don't have any more diagonal forces. Now this is going to cause us to have to adjust a few things in our free body diagram. Notice that now we have a downward friction force y component as well as our gravitation force. That means that the normal force that was being applied before isn't going to cut it. That normal force is going to have to be longer in the y dimension and therefore also longer in the x dimension, because in order for that force to be perpendicular to the slope still, it needs to extend more in both dimensions. And that means that our force triangle for the normal force is going to change slightly too, to a similar triangle that's a little bit larger than our original one. All right, and now we're ready to start analyzing what's going to happen. Notice that we just have a whole lot of forces here that we're going to have to keep straight in this problem. This is going to get pretty complicated. Let's get started. Here is what's going to happen when we add all of our forces together as a vector addition problem. Notice that the sum of the forces when added together is going to point toward the center of the circle in the direction of the centripetal force, and it's able to supply a pretty large centripetal force compared to our centripetal force before. That's what it looks like in vector form. Here's what it looks like in equation form. Here's our net force equation. It's the sum of all of these vectors. And then a bunch of these vectors are going to cancel out because they add up to 0. That would be my y dimension normal force, gravity, and the y dimension friction force are all y dimension forces. When added together, they cancel out. Then I'm also going to note that just like before, when I add these vectors together, I get a net centripetal force. Okay, and that's what this equation shows. And I can go ahead and combine these equations. So the x component of normal force plus the x component of the friction force. Notice that I have more force contributing to my centripetal force than I did before. That's going to equal the mass times the centripetal acceleration when I combine those two equations together. Now, just like before, those terms that I canceled aren't just completely canceled out of the problem. We can set them equal to 0 when we add them together in a y dimension part of the problem later on. For right now, let's still focus on the x dimension. So we have these expressions for what's happening in the x dimension. Most important one is that final expression, the normal force x component plus the friction force x component equals mass times centripetal acceleration. Do I know anything about the normal force and the friction force? Can I replace these x component expressions with expressions that actually have Fn and Ff in them instead of just the x component? Because I don't know what the x components of either of these are. Well, here's what I can do. I can note that the x component of the normal force is going to be Fn times the sine of theta. I can see that from the triangle at the bottom, that the x component is opposite that 10 degrees. So if I take the normal force times the sine of theta, now I have an expression for the x component of the normal force in terms of the actual normal force. And chances are I can figure out somehow what the actual normal force is in this problem. I have a much better chance of getting that than just the x component of it. Okay, what about the friction force? Well, you do the same sort of thing. The x component of the friction force is the friction force times the cosine of theta. I see that from that triangle on the left because the x component is adjacent to the 10-degree angle there. So I will use the cosine function. And I also know that Ff, the friction force, is equal to mu times the normal force. Here I'm talking about the coefficient of static friction. And I'm given what that is in this problem. Okay, so again, I'm relating this back to the normal force. And the coefficient of static friction times the normal force is Ff. So I'm going to go ahead and replace Ff in that previous expression that has the cosine of theta in it. Ffx is equal to the static friction coefficient times the normal force times the cosine of theta. Now, if I go back to my expression for MA, when I combine those two equations together, notice in that expression before I had the x component of the normal force and the x component of the friction force added together. I'm going to add together these more complicated expressions, but these expressions now bring in the actual forces instead of components of the forces, and that's going to be helpful. I'm also going to choose a centripetal acceleration expression right away like we did before, and once again, because we're looking for the speed that I can travel around the curve, I'm just going to go ahead and use that the centripetal acceleration is the velocity squared divided by the radius. Now I'm going to plug all of these values substituted into our combined net force equation, and I'll get an equation that looks like this. It's a pretty complicated equation. I can take one step to simplify this and get the normal force factored out on the left. So it's the normal force times the sine of theta plus the coefficient of static friction times the cosine of theta equals mv squared over r. Now let's just think about what I know. I know theta and I know the coefficient of friction. So I could solve that entire term in parentheses on the left. I know the mass of the car. I know the radius of the curve, but I don't know the speed that I'm looking for. I have two unknowns here. So I'm going to need to figure out what one of these unknown values is, and I'll bet I can figure out the normal force somehow. In fact, I am so confident that I'm going to get the normal force on a side by itself, and later on I'm going to use a substitution to plug something else in for the normal force here. So see that this equation is just rearranged so that the normal force is on a side by itself. Then I have all my other terms on the other side, but I still have two unknowns. I need to figure out what that normal force is, but it's not as easy as it was before when there was no friction, because when there was no friction, the y component of the normal force was just opposite of gravity, and then I could use trig to figure out what the actual normal force here. But in this case, I have three forces in the y dimension. I have the y component of the normal force, gravity, and I also have the y component of the friction force, because the friction force is pointing at an angle down the slope. And that complicates things. So if I added all of these together, I would get 0. But I'm just going to note once again that the large force, the y component of the normal force, must equal the sum of the two smaller forces pointing downward. And I'm just going to say that we're going to work with magnitudes. The magnitude of the gravity force and the magnitude of the friction force is y component. We're not going to worry about negative values. You can see from the diagram visually that this is going to work out. So for my next step, I can go ahead and do what I did in the last problem and replace Fg with mg, but I don't have any way of simplifying the force of friction in the y dimension straight out. But I can use that same relationship we used before from the friction force triangle and replace Ffy with the friction force times the sine of theta. And what will that do for me? Well, it allows me to replace the friction force with the values that we know. Mu times the normal force is the friction force. And then I have to include the sine of theta there as well. But I know mu. I don't know the normal force yet, but I know mu. That gets me a step closer, okay? And I know theta. So I still have an unknown here, the normal force. Okay, so I just replaced my friction force term in this equation. And I know that gravity force is mg. I know the mass and I know gravity. What about the y component of the normal force? So I can do the same thing I've done before. And I can note that the y component of the normal force is the normal force times the cosine of theta. And then I'm going to put that expression, the normal force times the cosine of theta, and my expression mg, and my expression static friction, coefficient of friction times the normal force times the sine of theta. I'm going to put that all into my expression where I have these three forces equal to one another. Okay? Now, what can I do with this? Again, this looks like a pretty messy expression. Well, what if I get the terms that have the normal force on a side by themselves? And then I just have mg on the other side because it doesn't have a normal force in it. Well, now I can factor out the normal force. Once I factor it out, I have that normal force times the cosine of theta minus the coefficient of static friction times the sine of theta equals mass times acceleration due to gravity. And this is a really functional equation because what don't I know in this equation? I know theta, I know the coefficient of static friction, I know the mass, and I know acceleration due to gravity. The only thing I don't know here is the normal force. So I could, from this, calculate what the normal force is by simply rearranging this equation and getting the normal force on a side by itself. But now, if I have that previous expression that includes the normal force, and I have this expression that includes the normal force, and notice that I have the normal force on one side of both of these expressions, they both equal the normal force, I can actually set these two expressions equal to one another. And that's what I'm going to do. When I set them equal to one another, I realize that the mass actually cancels out of this problem. It's in the numerator on both sides, and it's the mass of the car. So I don't even need to know the mass of the car, even though it's given in the problem. I would just be multiplying both sides by 1,000, and it's going to cancel out in the end anyway. The next thing that I'm going to do is get v squared on a side by itself because that's what I'm solving for. So I'm going to multiply both sides by the expression in the denominator on the left. And you'll notice that I have a pretty complicated expression here for the velocity, the maximum velocity around which I can drive around this curve and not slide because of static friction. We're going to clean this up just a bit, but you're going to see that even once we clean this up, this is still going to be a pretty messy expression. Let's see, to clean this up, what I'm going to do is I'm going to factor out of the denominator an expression, the cosine of theta. And I'm going to factor out of the numerator an expression, the sine of theta. Okay? So if I factor the cosine of theta out of the denominator, well, if I, first of all, divide the cosine of theta by the cosine of theta, that's going to give me 1. And if I divide the expression, the coefficient of static friction times the sine of theta by the cosine of theta, I'm just going to have that express sine of theta over cosine of theta. And you're going to recognize why that's, you probably already recognize why that's a relevant expression. In the numerator, I'm going to do the same thing. I'm going to factor out a sine of theta. So sine of theta divided by the sine of theta is 1. You'll see that there's a 1 in the parentheses there. Plus, and then I'm just going to divide that second term by the sine of theta, so I can pull that sine of theta out front. And in that expression, I have cosine of theta divided by the sine of theta. Notice that's the inverse of the expression down below, and you'll see why that's relevant in a bit. Well, I'm just going to note that I have some trigonometric expressions here that I know how to combine. Anywhere I have a sine of theta divided by cosine of theta, I know that's going to be a tangent of theta. And then cosine divided by sine is just going to be the flipped over version of that. It's going to be the cotangent of theta. Okay, so let's go ahead and replace those things in those green boxes with their correct expressions. So I'm going to replace the sine divided by the cosine with tan theta, and cosine divided by sine with the cotangent of theta. And this doesn't really look all that simplified, except when you realize that in the numerator now, I can distribute that tan theta back into the expression. And when I do that, I'm going to have the tangent of theta times 1 is just the tangent of theta. But then that second expression, the coefficient of friction times the cotangent of theta, when I multiply that by the tangent of theta, the cotangent times the tangent is just going to equal 1. So I get rid of that cotangent in there. And this is a slightly cleaned up version of this. Now, why is this useful? Well, I have everything in terms of the tangent of theta. I don't have sine and cosine of theta. And because everything's in terms of one trigonometric expression, if I wanted to solve for the angle using this expression, I could get the tangent of theta on a side by itself by getting all terms that have the tangent of theta in them onto one side of the expression. That's why this was useful. That's why I did that little extra last step. I didn't really have to because I know theta, so I could have just plugged it in everywhere that there was a theta and solved. But now I have a much more useful expression because theta's in terms of the tangent of theta in both places. Same thing with the coefficient of static friction. If I wanted to solve for the coefficient of static friction required to keep a car moving around a curve with a certain bank angle, I could get the coefficient of static friction terms on a side by themselves, factor out the coefficient of static friction, solve for that term. So this is a pretty useful equation overall, but what we need to use it for is exactly what it's set up for right now. I need to solve for the maximum speed that I'm able to take this curve. And to do that, I'm just going to plug in values. I'm going to plug in G, plug in R, 10 degrees is theta. I'm going to plug in my coefficient of static friction on the top. On the bottom, I plug in theta again on the bottom. And when I evaluate this unwieldy expression here, I find that and remember, I have to take the square root of that all at the end. I find that the maximum speed with which I can take this curve is 34.4 meters per second. Now remember, up above, it says I can take this at 125 kilometers per hour. You might remember from the earlier part, we simplified 125 kilometers per hour. We converted it, to meters per second and found that it was 34.7 meters per second. Let's just verify that, and we'll convert 34.4 meters per second to kilometers per hour and see how these compare. So if I multiply by 1 over 1,000, and then by 3,600 over 1, I find that my speed is 124 kilometers per hour. That's the maximum speed that I'm able to take this curve without sliding. That's what I calculated. Now my reference speed, the speed that I actually am moving around the curve, is 125 kilometers per hour. And how does that compare to the maximum speed? Well, it's greater. So I'm moving just too fast and my tires are going to start squealing as I move around this curve. I'm probably still going to stay in my lane because I'm not moving that much faster, but my tires are going to start squealing as I move around the curve because the friction force isn't great enough to provide enough centripetal force along with the bank of the curve to hold me in that circle without sliding. So yes, the car will skid a little bit. It's probably not going to skid all the way off the road, but the tires are going to start squealing as I turn this corner. All right, that was a complicated derivation, but you should be able to do complicated derivations because we didn't do anything unlike things we've done before. We used free body diagrams, We used vector addition problems. And all that we did in this problem was we solved in the x dimension first to find that we had an equation with two unknowns. Then we solved in the y dimension, and we evaluate the unknown, one of the unknowns in our previous expression, and that left us with the only actual unknown was the thing that we were looking for, the tangential velocity. So then we went through the process of plugging this all in. Honestly, you could have evaluated the expressions as you went. That would have made things a lot easier. So you could have just plugged in the 10 degrees for theta all along and figured out what the cosine and the sine of 10 degrees were. And that would have allowed you to evaluate the expression for this particular problem as we go. However, what we did was we developed a general equation that works in a lot of different situations that tells us information about the angle of a banked curve, tells us about the maximum speed that we're able to go around that banked curve and the radius of the curve. And we can plug in generic values to that expression to calculate for different things. And now you know a bit more specifically about setting up uniform circular motion problems when that uniform circular motion is caused by a centripetal force on an incline.